Hi there, welcome back. Welcome back to the channel, and I hope you've had a great new year. I hope this year brings us all great stuff, better than the last. But we're back to work. No rest for the wicked. Actually, it's been quite restful. This holiday season has been a lot of rest. We weren't allowed to really go out much, so it's been restful. So I guess I haven't been wicked enough. But I hope you have, and I hope you've enjoyed it. Back to the series on the Grundig 2147. I want to carry on where I left off last time. It's the FM alignment and the description of the FM circuit. Just to follow on, having done the description of the AM circuit, I tried to do something different. I actually tried to shorten it. I wasn't successful. So what I'm going to do is I'm going to put a notice here and tell you where the description ends. So if you want to skip straight through to the actual alignment, please go ahead. I won't hold it against you. So I hope you stick around and enjoy the video. Sometimes one of the most daunting things about looking at a schematic like this is the absolute complexity of it. You see just too much, and trying to understand, if you don't understand this clearly, can be quite difficult. So what I do sometimes, especially when I'm trying to clarify how something works, is clean it up. Now, how do you do that? Well, you basically put this into something like Photoshop, and you clean up all the stuff you don't need on the schematic. Like this, for example, looks a hell of a lot better. You've got things a lot clearer, you don't have all the clutter at the top. But now I want to go one step further. Now I want to look at just the FM circuit. Now it gets a little bit more challenging. I've still got this whole mess over here, which is the audio section, the AM section. So can I make it a little bit clearer? I think I can. How's that? Now that is clear. So what have I done here? I've removed everything that is superfluous to the explanation or the understanding of the schematic. I've removed the audio section, the power amp and preamp section over here. We don't need to look at that because we understand that already. I've removed everything to do with the AM. And you can do that quite easily because there are a few switches like this one over here, which you can select FM or AM, which means that if you've selected FM, all the AM is basically gone. So I erase it and I activate all the switches that are related to FM, make sure you've got that done. And I also remove components that are not seen by the FM, like this IF transformer for the AM section. Now when I look at this and I want to understand how the FM section works, I've got something that's a little bit more manageable. So let's start looking at this FM circuit and figure out how this thing works. It's still a little bit daunting, but again we'll break it down into little chunks and eat the elephant a steak at a time. We'll start with the antenna, obviously. And if we look at this antenna, which is sitting outside, it's a dipole usually, you've got the entire spectrum really is passing across that antenna, and you're picking up whatever this antenna is resonant to, which is usually a band of frequencies, and you want it to be the frequency range of your FM band. So the first stage you meet is actually no more than an RF amplifier. This level is very small, so you want to increase it, and that's basically all you do. Your signals come in here, through that coil. There's a little filter there which cuts out a lot of the much higher frequencies, but that resonates across, or that creates a voltage, a signal voltage across that coil, which is actually a half of a transformer. It's the primary of the first transformer there. That secondary receives that signal by transformer action, and it feeds it into the cathode circuit of this triode. This is half of that front end tube, which is the ECC85. And the signal is being fed at the cathode, which means that it is amplified but not phase inverted. If you'd fed it into the grid, it would be phase inverted. This grid is actually grounded through that 100K resistor. So it's going into the cathode, it's amplified, not phase inverted, and it goes along here and it gets to there. Now what you've got here is all the frequencies that you managed to pick up, pass through that transformer and amplify, which is basically the entire FM band, and probably quite a bit beyond that and below that as well. So what do you do next? Well, next you meet a tuning front-end circuit. This is a tank circuit. It's made up of that tuning capacitor. That is a half of the tuning capacitor that's inside that FM can at the front. There's a capacitive trimmer, which is to adjust the limits of that capacitor, and there's a coil. So this is a tank circuit, and the purpose of this is to pre-select the station that you want to listen to. In other words, to tune to your 88 megahertz station, your 91 megahertz station, or, as is the example we're going to use here, a 100 megahertz station, for argument's sake. So here's our 100 megahertz station being tuned to. This signal is now being filtered from all that rubbish that's coming in. That signal then comes into this section of the circuit. And what does it meet? It's a local oscillator, so it creates a stable frequency which you can adjust with the other half of that tuning condenser. You tune that there, and you've got a coil. So this is basically a tank circuit with the effect of this triode, which is the other half of the front end tube. There's one half, there's the other. You create an oscillator, and this oscillator varies depending on where that capacitor is. Now that capacitor varies in harmony with that one there. So when you tune the front end, you're tuning the oscillator, which means when you tune the front end, you're adjusting the local oscillator frequency. And the idea is, and the convention is, that whatever frequency you've tuned to the front here, this circuit here will tune to an equivalent frequency of 10.7 megahertz higher. So if I've tuned to 100 megahertz here, in the same position of the tuning condenser, this oscillator section will produce an equivalent frequency of exactly 110.7 megahertz. If you drop 2 megahertz there, you'll drop 2 megahertz here. Now that's quite neat. And the reason is because these two frequencies have to be put into a blender to a section or a function of this tube called a mixer. This tube is receiving both of those frequencies. It's receiving the 100 megahertz here through this coil and into the grid. It's receiving this thing, and it's actually producing this 110.7 megahertz in this oscillator circuit. It needs gain to oscillate, and that's where the gain comes from. So it's producing 110.7. But the other thing that this tube does, by virtue of these frequencies coming in, is that it blends them, mixes them, and produces a series of new frequencies, which are actually quite a cocktail. As you can see over here, coming out of here, out of the anode of this tube, you've got 100 megahertz, which is the one that's coming in. You've got 110.7, which it is producing, and it's the local oscillator frequency. You've got the sum of the two, and more importantly, you've got the difference of the two. Now this is the key. This is the entire key to this whole circuit, is that you produce a frequency which is the difference between what you're tuning to and what your local oscillator is producing. Because if you look at this, if you increase that by 2 megahertz, that will increase by 2 megahertz. So that'll be 102. That'll be 112.7. That will be 212.7. However, if you subtract that one from that one, you will always have 10.7 megahertz. So you've created a fixed frequency. What you've actually got here is you've got 10.7 megahertz that then gets fed on to the next section of the circuit. It comes out of there, in fact all of them come out of there, into this primary of this IF transformer. They're actually two coils in near vicinity to each other, and they resonate with each other. So you tune this coil here, F, to resonate at 10.7 megahertz, and that means that all the other frequencies are ignored. They're not seen, they're not amplified at all. They're certainly not passed through to the secondary, which is what this one does. Now, if your secondary now is also tuned to 10.7 megahertz, which it is, what you get is a signal coming out of here, which is precisely the 10.7 megahertz that you want. But more than that, it's the 10.7 megahertz that you want that's got modulated on it, frequency modulated on it, the information that this carrier is carrying here. In other words, your radio station is now sitting on a 10.7 megahertz carrier as opposed to sitting on a 100 megahertz carrier. We've reduced everything to a manageable, quantifiable and known figure, known carrier, which is your 10.7 megahertz, and that is your IF frequency, and it goes into the grid of that tube through this switch over here, which is the selection between FM and AM. We've set it to FM, so it goes straight into the grid of that tube. And we can carry on from here. So here we are. We are at the ECH81, which, if you recall, if you were awake through the last video, and I really commend you for that if you were, this thing was the local oscillator and mixer tube for the AM. However, for FM, everything else has disappeared. As you can see, all that stuff is gone. And this thing now has another function. And its function with FM is purely as an IF amplifier. It takes that 10.7 megahertz, and all you're seeing here is an amplifier. This is the anode, this is the B plus coming from the bottom here. So between them, if you follow that, you've got a tank circuit. There we go, you've got that tank circuit. And so that is a load to this IF amplifier. And it's a load that is tunable. And it's tunable and tuned to the frequency that we want, the 10.7 megahertz, which is what we want to pass through. And that's what we get. We've got our first IF transformer. This is really the first one, but these are actually just two coils in close proximity. This is actually that IF transformer. Now, the primary is tuned to 10.7 megahertz, which means that at that frequency, it's got the highest impedance. So what you have is that at that frequency, the signal goes through, and the secondary on this side is also tuned to 10.7 megahertz. So the signal is picked up. Reference to ground over here, see that? The signal is picked up and fed to the grid of that tube. So in this case, both of these sections, both of these coils in this IF transformer are tuned to let through 10.7 megahertz, your IF frequency, which you pass through to an EF89 tube. Now what does that one do? Well, you can guess. That is the second IF amplifier. First one here, second one here. So this is actually the IF amplifier that is an IF amplifier both for FM and AM. But for the FM, that's what it's doing. It takes that 10.7 in a similar way to that one, and it passes it through, amplifies it through to this coil. It's amplifying it because it too is the load between the B plus, which is down here, goes up there, to the anode. So this is the load of that tube, and it passes that signal that we want, the 10.7 megahertz, with the station modulated on it. It actually resonates at that frequency and will allow that to go through. What we have there is still our 10.7 megahertz, which is our IF frequency, and that's going through to that section. It's the primary of our transformer here, and this transformer is actually a discriminator transformer. It comes from the Foster-Seeley circuit. The name stayed, but it's a discriminator transformer, and it has a few characteristics that are different to the other ones. You don't tune this one to 10.7. I'll explain that in a second. This transformer actually has a primary, a secondary, and a tertiary coil. But the tertiary coil, this one here, is actually part of the secondary circuit, but it is wound on top of the primary circuit so that it actually induces a voltage, a signal here, which is perfectly in phase with that one. And this phase is what's going to work against the phases of those two signals to produce our audio in a section called our ratio detector. Now, there are various types of detector circuits. I mentioned the Foster-Seeley, where this transformer name came from, the discriminator. This one is a ratio detector. You get a slope detector. You get quite a few. I'm not going to go, and I don't even know all of them from these old circuits. But this one is the most popular one that I've come across. It's an unbalanced ratio detector. You can also get the balanced version. The way it works is quite fascinating. You should read that up. I'm not going to go into a lecture here on it. Quite honestly, I had to read up again because these things sort of slip your mind if you don't keep up with them. And I had to read up again. It makes perfect sense. It's a beautiful circuit, beautiful. And it's more appealing, especially because of the tube that it uses. This particular tube, the EABC-80, has got 3 diodes and a triode. Now, this ratio detector needs 2 diodes, and it uses that one and that one. The other diode is actually used for the AM detection, and the triode is used for the audio preamplification. So that's quite dramatic. That's quite amazing what this one tube can do. And the result of all this is that we have a signal, an audio signal, stripped off from that carrier. Remember, that carrier had frequency modulated on it, our radio station, our audio. Now, what this does is it produces, as a result, down here, our audio. And that is the holy grail of everything we've been doing. We've been trying to get audio out of this. And as you can see, if we look at it like this, that audio comes down here into that switching system through a DC blocking capacitor, and it ends up at the top of the volume pot, which is the target for all audio in the system, be it AM, FM, or pickup input. And that's our detector. That's how that works. And we are nearly there, because now I need to explain how it is that we actually peak those transformers that I've been talking about. The way to do that is to measure a voltage across this capacitor here. Now this capacitor, this is the detector cap. It's an electrolytic capacitor. It's strange because it's actually got its positive connected to ground, and its negative goes up to there. And the reason is that this detector, ratio detector circuit, produces a negative DC voltage which is proportional, or nearly proportional, to the strength of that carrier coming through here, of that IF frequency. Which means that if you can measure that voltage, it'll be negative DC, but it's just a DC voltage. If you can measure that voltage, you'll know when you've peaked these coils as you turn them, all of them that I've mentioned. So what you need to do is you need to use a voltmeter. And your voltmeter is connected to that side of the capacitor, in other words, the negative side of the capacitor, and to that side of the capacitor, which is ground. So you put your voltmeter across there, and you will see a DC voltage, which will be negative, and you will adjust your coils, these coils, that one and the other coils, till this thing peaks, and you'll see this sort of move right and left. You'll maximize the negative DC voltage as you turn those coils. And the way to do that is you feed a signal. They tell you to first feed a carrier into here. And it makes sense. If you fed a carrier of 10.7 megahertz with no modulation, you're just trying to get the coils tuned to pass the carrier frequency through. If you put a 10.7 megahertz signal here, that means that this thing will amplify it, and you can peak that coil by seeing whether you've got your maximum DC voltage coming across this capacitor. So you peak that one. Then you take your signal from here, from the grid of the EF89, and you move it one step back to here, to the input, to the grid of this ECH81. And you do the same to both of these transformers. You peak them, reading a voltmeter at the end there, at 10.7 megahertz. You peak them so you get the maximum negative DC voltage, okay? Then you got one more step to do, and that means you've got to go back, and you've got to peak this guy over here, or these two really, okay? Now how do you get 10.7 megahertz into this? Well, you could feed it into here, but I'll challenge you to try and find the grid of that tube without messing up that circuit. So the best way to do this, because this thing has got so much gain, remember, this has actually got some gain, that IF amplifier's got gain, and that IF amplifier's got gain. So the signals that you're putting in progressively backwards need to be progressively smaller. And from this stage onwards, there's so much gain that all you need to do is to lightly couple this signal onto your mixer tube. And the way to lightly couple it is to take a signal generator producing a 10.7 megahertz and wrap it or connect it to a wire that's wrapped around the coil, literally like a small coil on the outside of that tube glass, and that'll get through. And you'll see, depending on what amplitude you give this signal, you will see that it actually gets through to the other end. Now, you can also, as in the case of this radio, you can also use the shield. There's a metal shield that's around that tube, and that shield is grounded. You desolder the ground connection, and you can actually clip your signal generator's signal line to the shield, which then induces it into the tube, and the negative of your signal generator goes to the chassis, which is ground. So you're feeding it in here, you adjust those two, and you adjust that one for a maximum DC voltage over here, always at 10.7 megahertz. Now, how do you adjust this last one? Well, this last one is interesting because this last one is actually the most important one in the entire circuit, provided you get a signal through. And it's the one that actually balances this ratio detector. It balances the two diodes, the action of the two diodes in here. And it balances it by the amount of inductance that you put in here, because it'll change the phasing in here. So when you adjust this, what you're doing is you're actually preparing this circuit to give you a good detection, an optimum detection of the audio signal that's coming on your carrier, on your IF frequency carrier in this case, to produce a good quality signal of audio here. So one way of doing it, the easiest way for me anyway, is to feed that carrier at the front end like I've just described, but modulated with an audio tone on it, like a 1 kilohertz tone, or a 600 hertz tone, or a 400 hertz tone, one that you can hear. And when you modulate it and feed it through, because it's the audio that's on that carrier, it'll come out here as audio, it'll go through your preamp and your amplifier and come out your speakers, okay? So what you can then do is connect an oscilloscope to your speakers, see the sine wave, that audio sine wave on the screen of the oscilloscope, and tweak this guy till you get the best looking sine wave. In other words, the one with the least amount of distortion. And that's how I usually do it. And I've found that it's pretty damn good enough, okay? There is another way, and the other way is a little bit more complex. In fact, there are quite a few other ways, but the one that I've used also is this one. The way this works requires that you read up on how this works, the entire ratio detector works, but I'll just tell you how you do the testing or the adjustment. What you do is you fix two resistors in series. You solder them in series, okay? Usually with croc clips on the end, which is what I've got here. So you've got 200K resistors. These can be anything from, well, actually anything greater than just about 1.5 times that value there. Because what you do is you put this thing across from there to ground. In other words, across really that load resistor, that 56K resistor. You're just putting these two in series across them. So as it is here, you've got 200K across 56K, all right, in parallel with. Remember, this one's at ground, so that one can be just chassis, ground, right? Now, the value of these resistors isn't that important. Their precision with regard to each other is very important. To get a good balance, you need very accurate resistors in value with relation to each other. So you measure them. Get two that are as close as possible in value, and you solder them together. And you clip them like that to the top end there and to ground. So you've got that. Then you connect a microammeter. It's a very small voltage or current that you're going to get here. So you connect this meter. I've got a meter here which is 10 microamps range. There's 100 microamps range. You connect that between, or to the point of intersection of those two resistors, between it and the audio signal here, the output really of the discriminator transformer, or rather of the ratio detector. That's the output. That's where your audio comes out. There we go. Comes out here. So you connect that between there and there. And you will get either a positive current or a negative current. So the recommendation here is that you usually use one of those meters that is 0 in the center, or that you can set it as 0 in the center. And if it's negative, it swings left. And if it's positive, it swings right. So what you're trying to do is to get it to the 0 point, the null point. And when you get it to the null point, and I will show you here, when you get it to the null point, that is supposedly, should be perfectly aligned. So you should be seeing that perfect sine wave on your screen if you've got both of them connected, if you're doing it both ways. So I'm going to be doing that just to check my alignment visually. I'll be doing that with the meter. So that's how I do the alignment of the FM. There's actually a pretty impressive way, the best way, which is the real visual alignment, which is using a wobulator or a sweep generator and oscilloscope. I have not been able to get a decent signal from that here for some reason. I've done it with other systems. On this one, for some reason, I just couldn't get a decent result. So I'm skipping that version for this one. If I get a radio that behaves itself in the future, I'll do it. I can't honestly say I know why it's doing that. I don't. So I'm using two methods. One is the visual on the scope and the other one is the microammeter connected to the intersection of those two resistors. So that, my friends, is the description of the FM function on this particular radio, the Grundig 2147. It also describes how you align the IF. And I hope I haven't forgotten anything. And more importantly, I hope I haven't got something seriously wrong. If I do appreciate you calling me out on that in the comments. Well, enough blab. Time to get this thing done. Here we go. I've selected FM. I have the analog voltmeter and the digital voltmeter connected to the negative of that ratio capacitor. I just want the digital voltmeter as a second reference. The negative of the meter is connected to chassis, which is ground. I have the signal generator ready. It's producing a 10.7 megahertz signal at 40 millivolts RMS. You'll see why in a second. If you recall, I said that the signal generator was lightly coupled to that screen of the ECC85. There it is. The red crocodile clip is on the screen and the black is to the chassis. And I've got the analog voltmeter over here on DC volts. It's on a 3 volt range. The signal I'm getting at the moment is about 1.5 volts. Now the idea is to try and keep it below about 2 volts so that the AGC circuit does not kick in. That's pretty important. Otherwise you'll get a distortion of the adjustments. First thing I'm going to do is I'm going to unwind core B. Now B is that discriminator nulling one, the underside. That's the one you adjust for fidelity. And it's always a good idea to just unwind it so that it doesn't actually affect the tuning of the remaining cores. I sometimes do it, I sometimes don't. In fact, I sometimes forget, which is not a good excuse. But let's see. It's that one over there. These are ceramic screwdrivers. You don't want to go in there with metal screwdrivers at all for various reasons. One of them is you get shocked. So I'm just bringing it out quite a lot, actually, almost to the point where it's coming out of the former. Okay. Now we will adjust core A, which is at the top. And we adjust for a maximum negative voltage. The DC voltmeter there, the analog voltmeter, is set to negative volts. Oh, wrong way. There's a peak. That's peaked. Done. Now I'm going to go to the first IF transformer. That was the second IF transformer, and I'm going to adjust the top core. Wrong way again. Oh, that is quite a change. Get some of the wax out of here. There's my peak. That's peaked. Now I go to the underside one. I did remove some of the wax before. Try and get this to, there we go. It's pretty much peaked. That is peaked. And now I've got to go to the side ones. And according to the drawing we have, it should be these two over here. Let me just check that. E and F, yes. There's my peak. And now this one. There's my peak. Actually, came out of it. Okay. I do believe I've peaked that. Yep. I've peaked that. Now, all I need to do is I'll go through them again, make sure that I can't get a few more dBs out of it, or tens of dBs out of it, and then we'll consider the IF alignment with the exception of that final core, that final secondary, done. Now, I've got my signal generator producing that 10.7 megahertz signal, the carrier, and I've got a 1 kilohertz sine wave modulated on it. So if I put the volume up, I can actually hear it, which is sort of surprising because that core was almost completely removed. But we can see it on the scope. Now I'm going to start going down. Boom. See, it went through a phase there where it actually got higher. It was still distorted. Then it gets quiet, and then suddenly there's our sine wave, and it starts getting worse if I carry on through. So I know it's there. Now, I can get pretty loud here, but all I need to do is to adjust it for the best sine wave. There's my best sine wave. Now if I carry on going, it just gets worse. There it is. That's sort of the best sine wave that I could get on there without blowing my ears out. So we've actually aligned that, but we can check. And the way to check that is we actually remove the modulation. So there's no modulation anymore. And we need to connect something else here now. And what we connect is this. It's two resistors in there, 100K each. They're pretty exactly matched. And they meet in the middle. And they've got two crocodile clips. Now all I need to do is clip one of these there and there. Now I take my microamp meter, I'm going to put it on 100 microamps, and I'm going to connect this to the intersection of those 2 points, of those 2 resistors. So I'm going to connect that to there. Now the negative of the microamp meter has got to be connected to the audio out of the FM, and I happen to know that it's that guy over there. Okay. Now, when I look at this, I've actually got a small current there. So if I adjust it, I need to get 0. Watch this. If I adjust this way, it goes up. It goes down to 0. I'm going back. Now, because I don't have the center null or center 0, I can change the polarity of the meter to negative DC. If I carry on, it'll go up the other side. But I need to leave it exactly there. Just a slight twiggle. Just a twitch. There we go. Checking from the top so we don't get parallax. This thing is now exactly nulled. And let's see. If I give it modulation, I need to remove this because it's actually acting as an aerial and picking up noise. There's my perfect sine wave. Pretty good. So I've checked the alignment. So what exactly have we achieved with that alignment? Is this thing any good? Let's listen.
Uma gripe pode ficar com a impressão que pode não ser uma gripe e tal, e pronto. Lá estão os hospitais entupidos.
Já agora, já que estou aqui a falar no fórum uma vez mais, um terreno que é novo para a União Europeia. E como tal, este terreno vai sendo ocupado e a União Europeia e a construção europeia, mesmo antes da existência da União, sempre económica.
Well, unfortunately, I can't really play any music, but as you can see, it's become quite sensitive. And the quality of sound is exceptional. So I'm happy, and bear in mind I'm using this little speaker for now, so it should sound a lot better inside the cabinet. Now there's something else that I did which I want to show you. I did some measurements before and after the alignment, and what I did was I set it up and determined that 60 millivolts going into that shield was the level I needed to get around 2 volts maximum reading, and I read this with a voltmeter, so this was not a sweep. This was actually adjusting every 50 kilohertz, taking a reading and putting it into a spreadsheet, and the result was the graph. The first one, which was the before reading, was at 60 millivolts, and I got that shape. Now, when I finished doing the alignment, I found that I needed only 44 millivolts, 44 millivolts, to get approximately the same maximum of 2 volts. And you can see the result of that. It's slightly sharper. There's a hump on the one end, which is still there, and I can't really figure out why, but that's still there. But to see whether the sensitivity had actually increased, what I did was I then fed it with 60 millivolts, which was the same voltage that I had before the alignment, and that's the result. You can see that the sensitivity has actually gone up quite dramatically, because it's the same shape as the 44 millivolt one, but raised up, which tells us that even at that voltage, the AGC is not kicking in. But it's always satisfying to see a result like this, where you actually measure before and after. It's like losing weight. It really gives you a clear indication of whether you've done anything right or whether you've done anything different to make a difference. And this one certainly looks like I have. So I'm very pleased with that, and so pleased in fact that I decided that this radio couldn't live by itself, so I needed to get it a twin brother. And this one arrived. This is the brown version. It's also in very, very good shape cosmetically. I don't know what the inside is like. I haven't switched it on. But for some reason, I really like this look, and I decided I wanted to get one of each. And what you don't know is that there's another one on its way. I found another one. I couldn't resist. The price was very good, so I decided to get that as well in case I need spares. And I may well do, especially if that guy needs to be replaced. Now, I'm picking up AM. That's actually on the AM, so I'm picking it up quite well. I'm going to try and rewind it. I haven't forgotten about it, but I just haven't done it yet. But if I do need to replace it, I'll have a spare coil. Yeah, fill the house up with Grundig 2147s, why don't you? So that's where I'll leave you for now. I hope you've enjoyed this video. If you have, click like, share, subscribe, and all that jazz. And I'll see you back soon with the next video on this series. We aren't finished yet. Thanks for watching. Bye for now, and stay safe.